Hi, and welcome to Radiation Lesson 4, Graphical Exponentials. Fairly short video today, so I'm aware it's your last one before half term. What we're going to be looking at today is this e to the minus lambda t and how that affects different things, and we're going to finish with a short proof of why this is the equation for our half-life. So, just to recap, remember lambda is our decay constant. That means in 1 second, how likely is it that one particle will decay? So it's per unit time, but it's always a second. So, all of the different properties of our lump of radioactive materials, let's imagine we've got a kilogram of uranium, all affected by this factor, e to the minus lambda t, minus because they're all getting small. So what do I mean by properties of our lump of uranium? Well, there are three. We've got n, which is the number of particles. And the way to work this out, remember, is to work out the molar mass of whatever it is you're dealing with and then multiply it by Avogadro's constant. We've also got A, which is the activity. So remember, that's the decays per second. And then finally we've got C, which is the count. So very, very similar to the activity. That's just if you put a Geiger Muller tube next to it, how many times is that going to click? All of them can be put on a graph. So this is N, A, or C relative to time, and they're all going to have the same shape, which is our exponential curve like this. Because if you think about it, it's got a half-life, which means it's got a set time to half, which is the very definition of what an exponential is. This also means we can express each of these through an equation. So the number of particles at time t is equal to the initial number of particles multiplied by e to the minus lambda t. That's also true of the activity at time t, initial activity, and the count at time t, the initial count. So all three of these will give the same shape of graph, and this point here would be where we started. This is, of course, very, very similar to our capacitor, but remember, when we've been through, this is going to have equal times to half, and we'll always talk about half-lives, whereas with capacitors it was that awkward 67% nonsense. The way you find the half-life, very, very simple. You go to half of whatever property it is, you go out to here, and this will be equal to 1 half-life. If you then went to quarter, boom, this will be equal to another half-life. Simple as that. So, there's one last thing you need to know for the exam, which is the proof of why the half-life is equal to natural log 2 over the decay constant. And the way that works is like this. Let us imagine that one half-life has gone by. So we are using the equation number of particles at any given time as our initial particles, e to the minus lambda t. So if we've been through one half-life, then by definition, we have half of whatever it is we started with. And that's going to be equal to the number we started with, equal to e minus lambda, and then we know our t is our half-life. So capital T with a little half, that's half-life. We can then cancel the n zeros, giving us half equals e to the minus lambda half-life. We then take the natural log of both sides, so ln a half equal to minus lambda t a half, half-life. Then we can use our little cheeky log rule here to turn ln a half into minus ln2, is minus lambda t to the half, and then we just rearrange those, get rid of our minuses, and that shows us that t half is equal to ln2 over lambda. Simples. Remember, the thing you might forget in the exam is this jump here from ln a half to minus ln2, but that's just using your log rules. So there you go. That's what they look like. That's how you calculate the graph. That's how all those three are. And this is our proof of why a half-life is equal to that. Enjoy your half term, and I'll see you after